Let me know if you have any questions before we get into content today. Keep up with the homeworks and the quizzes on WebAssign. You don't want to have to do too many of those all at once at the end of summer. Today we're going to focus on circuits, namely resistance circuits, what resistors do in a circuit. Tomorrow we'll cover electrical power, and Friday we should have a homework day. I think everything's working that time. I'm a little paranoid at this point. All right, so we've looked at some circuits before. The circuits that we've done some math for have mostly been, last chapter, we looked at capacitor circuits and what a capacitor functions as in a circuit, namely a power source or a reservoir of energy and electrons. We're going to shift gears and look at what resistors do together in circuits, similar to how capacitors can add up or reduce the overall effect capacitance of a circuit depending on how they're wired. Resistors are much the same way. Some of the logic is a little bit different. Some other things we're going to talk about is exactly what happens to all of the current in a circuit and all of the voltage in a circuit, because the configuration of a circuit kind of determines how current and how voltage get distributed to each specific component of the circuit. Some things to note before we move on to that. One, as a brief refresher of what we've been doing the past few days, we're going to be utilizing Ohm's law as we look at our resistor circuits here. That's the statement I equals voltage drop over R, alternatively V equals IR. This is the relationship between the voltage, current, and resistance of a circuit, but it can also be used to describe the relationship between the voltage drop across a single component of a circuit, the current through a single component of a circuit, and the resistance of that same single component. So we're going to be using Ohm's law here to examine not just circuits as a whole, but individual pieces of a circuit. So the one formula has those two different uses, and we're going to distinguish between them as we first look at circuits as an entire thing, and then look at what's happening uniquely for each piece of a circuit. Something else to be familiar with. These would be the first time that I've said this concept out loud, but I want to draw your attention to two things called Kirchhoff's laws. Namely, the Kirchhoff's laws tell us that if you build a battery circuit, so you have a 9-volt battery, and you are using that as the power source for your entire circuit, if that one 9-volt battery is the only source of voltage, then that makes the entire voltage drop across the entire circuit 9 volts. And within the circuit, each individual element of the circuit is going to kind of has the potential to get a different piece of that total voltage. That'll make more sense when we start looking at total diagrams. The main thing to know about Kirchhoff's voltage law is that whatever the battery voltage is, that needs to be the voltage drop of the entire circuit. That whole voltage will get used up in the circuit across one or multiple different resistors. But by the end of the circuit, the total amount of voltage utilized must be equal to the total voltage of the battery. Similarly, here we go. So that's Kirchhoff's voltage law. The directed sum of any potential differences of any voltage around any closed loop is zero. If a circuit is Right. If a circuit is closed, the voltage out of the battery is the voltage that has to go back into the battery. The entire battery's voltage will get used. The potential drop across the entire thing will be equal to the potential drop of the battery itself. Kirchhoff's current law is pretty similar. These are just two rules that kind of help us understand what's happening to the current and the voltage in a circuit. The current law tells us that however much current comes out of a battery, that same amount of current must travel through the whole thing and come back to the battery. If a circuit has 1 amp flowing through it, if 1 amp exits the battery to move through the circuit, 1 amp has to come back to the battery. This will become more important when we look at parallel circuits where the current can divide up and split before coming back together. Kirchhoff's current law tells us that the current must all come back together and it must equal the same value before it comes back to the battery. Both of these laws in tandem tell us that whatever comes out of the battery has to come back to the battery in the same amount. This is about power, which we will talk about later. So, let's begin looking at resistor configurations in circuits. Now, resistors, we've already talked about parallel and series circuits in relationship to capacitors. And those configurations are not unique solely to capacitors. You can wire any possible electrical component in parallel or in series to another component. So the parallel and series are just general terms for how two things are wired together in a circuit. Either they're together in one path or they are on branching paths from each other. So you can have capacitors in series or parallel. You can also have resistors in series and in parallel. The weird thing is that how you add up total capacitance in series or in parallel is opposite how you add up resistors in series or in parallel. So to start with, here we have a resistor circuit wired in series. We have the battery that feeds directly into one light bulb, which feeds directly into a second light bulb, and then back into the battery. One path, the current has to go through both bulbs. Where for capacitors in this configuration, when you have capacitors in series, you had to do the inverse sum of the I forgot how to speak English for a second there. Inverse sum of the reciprocals is how I described that when you were adding up capacitors in series. And that's because capacitors in series kind of work against one another. One of them kind of limits the current flow to the other one, and that reduces their overall effectiveness. For resistors in series, that logic is swapped, because resistors in series, a resistor exists to reduce the current flow of a circuit. It's an obstacle that the current has to overcome. And putting one obstacle after another just makes it harder for the current to flow. So by adding multiple resistors in series, so one right after the other, you are increasing the total resistance of the circuit. So say, get my marker out. If we had a 5 ohm resistor, 5 ohm light bulb, and a second 5 ohm light bulb, the current has to first go through the first one, where it encounters 5 ohms of difficulty. Then it goes to the second one, where it encounters 5 ohms of difficulty. That difficulty does stack. And so as a result, resistors in series, their total resistance actually adds up linearly, the same way that capacitors did in parallel. And it's just because the measurement of resistance and capacitance are kind of opposite one another. One of them is a measurement of how good something is. Lost my train of thought, sorry. The logic is inverted. So for series resistors, they add up normally linearly. And I find that that makes more sense because, again, the entire point of a resistor is it is an obstacle. Putting one obstacle after another makes things more difficult. This would be like trying to, in terms of pushing current through a resistor, imagine the circuit as just a long hallway that you're trying to get a bunch of people to go down. And each resistor, making it harder to do that, is kind of like a doorway reducing the width of the hallway. One door reducing the width of the hallway will already block and jam up a lot of people for a minute, but putting a second smaller door further down after everyone's gotten through the first door is just going to keep making it more difficult. It'll just keep slowing down the flow of traffic. So here, resistors in series, the difficulty adds up, the resistance adds up. This is, again, counter to how resistors act in parallel. The way that resistors act in parallel is the same way that capacitors act in series. So in this configuration, you have parallel circuit, battery could send current either through the first light bulb or through the second light bulb. The reason that, if you remember from the from capacitors in series, because capacitors in series added up this same way, inverse sum of the reciprocals. When capacitors added up that way, it reduced the total overall capacitance of the circuit. And here, in resistor circuits in parallel, arranging resistors like this also drives down the total resistance of this particular circuit. So let's say, for example, these are two different 10 ohm light bulbs. When you build a parallel circuit, by simple fact of making it parallel, you have given the current more options for where it can go. Imagine again sort of the hallway example for series circuits. If you have a long hallway and you put several small doors in series in that hallway, it's continuously going to make it harder to get people through that hallway. But if you instead built a hallway that had multiple pathways out, so there's multiple different branches that a person could go through, by virtue of there being more than one path, you've made it easier for people to get through this hallway. They don't all have to wait to get through one door and then they all have to wait to get through the next door. If a lot of people are getting jammed and blocked up going down this hallway, they can instead just go down the next hallway. The simple act of building a parallel circuit inherently reduces resistance because having more than one path to go inherently makes it easier for current to flow. Now the current all has to come back together before it hits the battery again, but this configuration always drives resistance down. As a quick sample calculation, if we were to try to find the total resistance of our two 10 ohm parallel resistors here, 1 over R equals 1 over 10 plus 1 over 10, that would give us 2 over 10, which we would then have to invert to find our R total. That would give us 10 over 2. So the total resistance of this particular circuit would be 5 ohms. That drove resistance down. Parallel circuits drive resistance down inherently, just automatically. So the math, like the formulas are the same between this and capacitors. It's just the logic is backwards. I tend to think that the way that the resistors work makes a little more inherent sense than the way that the capacitors worked. If you liked the capacitor version more, all you have to remember is that resistors work backwards compared to that. So with that in mind, let's begin looking at how the current and voltage flows through similar circuits of slightly different configuration. So here, in this example, we've built two circuits out of the exact same components. They both have a 9-volt battery, they both have a 2K resistor, they both have a 10K resistor. It's just one of them has the two resistors in series, one of them has the two resistors in parallel. Each of these circuits is going to have a different effective resistance just because of their construction. And because they have different effective resistances, there's going to be different amounts of current flowing through them. Again, I'm going to rewrite Ohm's law real quick. They have the same battery, but different resistances, different total resistances. So there's going to be a different amount of current flowing through each one. The parallel circuit will just automatically have a lower resistance than the series one. But there's a few more quirks to be aware of for each different circuit configuration. In a series circuit, for example, in series, the main hallmark of a series circuit is that current only has one path to travel through. What that means is, however much current is coming out of that battery, I'll just say 1 amp for simplicity's sake. If 1 amp is coming out of that battery, then every single part of that circuit is going to have 1 amp flowing through it until it comes back to the battery. Both resistors will have 1 amp moving through them. And it takes a different amount of voltage to push 1 amp of current through each of these resistors. The two resistors here, one of them is 5 times greater than the other. It takes 5 times more effort, 5 times more force, more pressure to push 1 amp of current through the bigger resistor than through the smaller resistor. The way that we mathematically represent this is that each of the different resistors has a different voltage drop. I tend to think of voltage in a circuit as kind of like a resource. Voltage comes from a battery, and it's kind of literally a battery, a built-up amount of pressure, of force that can push current through the different parts of the circuit. And it's going to take up a certain amount of that voltage to get the current through the smaller resistor, and it will take up more of that voltage to get the total current through the second resistor. It takes more effort to push the current through the harder obstacle. So, and we'll do examples. We will demonstrate this mathematically. The way that I've written it here on this slide is, in series, every circuit gets the same amount of current, but has a different voltage drop. In series, they all have to share the same current because they're all in a row. There's nowhere else for the current to go. But depending on the size of each resistor, it's going to take up a different amount of the pressure of the voltage resource to get the current through each one. So we say, physicists like to say, that in series, every component of the circuit, sorry, that should say resistor, sorry, every resistor gets the same amount of current but has a different voltage drop. This is contrasted to parallel circuits. In parallel, there is more than one pathway for the currents to flow through. It's like a split in a river. And if some of the current goes down one pathway, it literally can't go down the other pathway because if you're following the movement of a single electron here, if an electron goes down this first branch, it cannot also go down the second branch at the same time. Each electron is a single physical object. It can't be in two places at once. So in parallel, the current gets physically split. However much current the circuit as a whole gets, if we know the total circuit resistance, we can find the total circuit current. But however much current the whole circuit has, that current value gets split right here at this junction. So whatever that total current is, some of it will go down the first path and some of it will go down the second. That split in the current then has to reform right here before it goes back to the battery. So again, if 1 amp comes out of the battery, maybe 0.2 amps goes down this branch and 0.8 amps goes down the other. And they all have to add back together back into 1 amp before it rejoins the battery. So in parallel, the different branches get different shares of the total circuit current, because literally a parallel circuit splits the current up. Interestingly, they'll get different currents, but in parallel, these two specific resistors in parallel will actually get the same amount of voltage. Whereas in series, it's the same current and a different share of the voltage drop. Here, it's different shares of the total current, but the two resistors will have the same voltage drop. This can be a little hard to picture, and so I like to envision it kind of like a waterfall. In series, the voltage, the potential difference over the whole circuit, can kind of be seen as like the difference in height of a waterfall going over a cliff. So the total circuit voltage is the difference in potential from the beginning to the end. There's more potential up top, and it's naturally going to flow downhill to where it has less potential. And then the mechanics of the battery serve to get the water back up to the top to then flow again. In series, this is as if the waterfall has like multiple steps to it, kind of like a splash mountain, maybe. The first resistor is one step of the waterfall. The second resistor is a second step of the waterfall. The voltage drops a certain amount each time because a certain amount of the potential is needed to get the current through that particular battery. So in series, one after the other, they have different shares of the same total voltage drop. But in parallel, it's two different pathways that both, again, if this was a waterfall, it would be like one river splitting and then both split rivers falling the same distance. It's not two different segments it falls, one after the other. It's two different drops from the same height. You have, if it's a 9-volt battery, you've got 9 volts of potential here and 0 volts of potential here. So in the parallel configuration, both drops go from 9 to 0. Whereas in series, one drop might be like 3 volts and the next one might be 6 volts. Depends on like if we were using the waterfall analogy, it would be represented by physically how far does the waterfall each time. In parallel, both split paths fall the same distance as they drop. And then they're both at the lower potential zone once they're done with each resistor. In series, they drop one at a time. It's the same total distance of falling. It's the same total drop, but it's done in segments. It's the total current falling in segments instead of split current falling the same distance in two different pathways. I'm hoping this visual is helpful for how to describe this, and we're going to demonstrate this with math. I'm going to show you the math for this and why it works. I'm just trying to give you the best analogy that I can for it. The main thing to remember, the 2 points here, is that in series, each resistor gets the same amount of current but a different voltage drop. In parallel, each resistor has the same voltage drop but gets a different share of the total divided up current. So each different configuration just splits one of the two resources. Series splits up the voltage, parallel splits up the current. I find the series one easy to remember, and then the parallel one is always just the opposite logic. Let me know how this feels right now. We're gonna do examples that I'm hopeful will help all of this sink in. I'll take a second to pause if you have any thoughts. Okay, so these are the two circuits that we're going to do math for, the 9-volt battery and the two same resistors in different configurations. So using our formulas and the logic that we just talked about, we are going to find for each of these two different configurations the total resistance of the entire circuit, the total current traveling through each resistor, total resistance of the whole circuit, total current of the entire circuit, the voltage drop across each resistor, and the total amount of current that travels through each resistor in each configuration. We're going to start with the series circuit. So I've redrawn it here. We have our 9-volt battery. We have our two resistors in series. To find the total resistance of two resistors in series, we just add them up linearly. So 2k ohms plus 10k ohms will give us a grand total circuit resistance of 12k ohms. We can then use that total resistance to figure out what the total current throughout the circuit as a whole is. So using V equals IR, our 9 volts, and our resistance of 12 kilo ohms, 12,000 ohms, that's going to give us a total series current of 0.75 milliamps, 0.00075 amps. So a very small amount of current, which makes sense. Series circuits drive resistance up. Resistance being higher makes current smaller, and you kind of want the current to be small anyway because that makes it safer and less likely to hurt someone. So these two things right here represent, and I'm going to use a sigma for this, the resistance of the circuit as a whole and the current through the circuit as a whole. Similarly, the 9 volts up here also represents the voltage of the circuit as a whole. We're now going to look at how each of those things kind of gets divided up across the two resistors based on the configuration of this particular circuit. Now, in a series circuit, every single piece gets the same amount of current because the current has nowhere else to go. There's no branching pathways. The current has to go through one and then through the other. So we do know that both individual resistors, resistor 1 and resistor 2, will get the same amount as the total circuit current. We're now going to plug that total circuit current into a version of Ohm's law for each specific resistor to try to figure out how much voltage is needed to push that current through that particular resistor. So let's start with the 2K resistor here at the top. We know its specific resistance, and we do know the specific amount of current flowing through it. So we're going to use Ohm's law again, V equals IR. So we have the current times its specific resistance here. And that's going to give us a voltage drop of 1.5 volts. They both get the same amount of current. It's just this is the amount of voltage needed to get that total current through that first resistor. The second resistor, the 10K one, is 5 times bigger. So to find the voltage required to push the same current through it, we're going to multiply that total current times its increased resistance, 10,000 ohms, and that gives us 7.5 volts, literally 5 times more. This tells us two things. One, the resistor that is 5 times larger requires 5 times as much voltage to get the same amount of current pushed through it. It's literally 5 times harder to get through the door, so it takes 5 times as much effort to get the current through. Additionally, note that our two voltage drops here, 1.5 and 7.5, add back up to 9. It's a 9-volt battery, it's a 9-volt circuit, all 9 volts got used. The total voltage drop for the whole circuit is 9 volts. It's getting used up in stages. First, the 1.5 volts get used up first, pushing the current through the smaller resistor, and that leaves 7.5 volts left to push the current through the bigger one. So this is still the total voltage drop for the whole circuit. It's just in series, it's dropping in stages because it takes certain amounts of the voltage to get the same amount of current through different size resistors. So our statements from before track in series. The different components get the same current, different drops of the voltage, and the same amount of current and voltage that come out of the battery have to get used up or come back to the battery. Our logic tracks so far. Let me know how this feels. Let it sink in for a second before we look at the parallel version. So, the parallel version has kind of inverted logic. The resistors are going to add up different. The different resistors will have the same voltage drop, but they'll get different shares of the current instead. So here it is redrawn as a parallel circuit. Same two size resistors, but in parallel this time. That's going to change what their total effective resistance adds up to. Specifically, we're going to do 1 over our total equals 1 over 10K plus 1 over 2K. That's going to give us something to the effect of 6 over 10, which will invert to 10 over 6, which means our R total is going to be 1.67 kilo ohms. Note again, in parallel, the total resistance is smaller than the smaller of the two actual resistors. So, if the 2K resistor was just here by itself, total resistance would be 2K. Even though we've added a resistor bigger than it, that has driven resistance down, because by virtue of adding a second pathway, that makes it easier for the current to flow than if there was just the 2K by itself. So, the total parallel resistance is always smaller than the smallest of the resistors involved in the parallel circuit. Excuse me. So here's our total circuit resistance. We can use that to find the total circuit current. So V equals IR, total circuit voltage is 9. Solve for total circuit current. We're going to use the total circuit resistance we just found. And that's going to give us a total circuit current of 0.0054 amps. Note that comparing that to the previous example had a higher resistance. As a result, it has a smaller current. Here we have a smaller resistance and a bigger current. Resistance is down. It's literally just easier for more current to flow out of the battery. So here is our total circuit current. Now, we need to look at what the voltage drop and what the voltage drop across each resistor and the current flow through each specific unique resistor. So in parallel, each resistor gets the same voltage. That's again because the two drops here, both resistors are going to drop from 9 down to 0 at the same time. Two separate pathways over the same height of waterfall drop. So here, each specific resistor will get the full 9 volts. So the 9 volts is what they both share here. The total circuit drop is still 9 volts. It's just dropping across both resistors at the same time. So now, instead, since they'll both have a drop of 9 volts, we're going to see how much current will divide up and squeeze through each resistor based on that amount of voltage. So, first we'll do the 10K resistor. So, V equals IR, 9 volts across the 10K resistor equals the 10K's current times its resistance of 10,000 ohms. That's going to give us a current through this first resistor of 0.0009 amps, 0.9 milliamps. Note that that is less than the total circuit current. That makes sense. The current is going to split. Only some of it is going down that branch, so naturally the amount that it gets would be smaller than the circuit's total current. The second resistor also has a voltage drop of 9 volts, but it has a smaller resistance. It's a 2K instead. So 9 equals current 2 times 2000. Simplify that to get current 2 equals 0.0045 amps. Note that again, this is also smaller than the total circuit resistance. Sorry, the total circuit current, because again, it's dividing, so each one would have to get less than the overall circuit total. But two things to note are that one, more current went down the path of least resistance. More current went down the path of least resistance. The branch with the 2K has less resistance than the branch with the 10K. That means it's easier for current to flow down that pathway, so more of the current is naturally going to try to move in that direction. Again, if you think about different sized doors in a hallway, more people can fit through a bigger door, so more people are going to move to the bigger door. And if the bigger door gets blocked, then people will start moving to the smaller door. So, the path of least resistance always gets more of the current. This is, again, why rubberizing your wires and your cables can keep you safe from electric shock. Because if the cable is coated in rubber, it's the path of least resistance for the current to travel through is through the metal of the wire still. But note, even though this branch is the path of least resistance, some current still went down the other branch anyway. This is why still rubberized cables can still be dangerous. Because even if most of the current goes down the path of least resistance, some of it might still go down the increased path just because there's a different branch open, and sometimes if everything is going down the main pathway, it's easier for that little tiny bit of the current to go down a different pathway, which is why you can still get shocked holding a rubberized wire, depending on what the voltage and current are, and depending on, well, how thick the rubber lining is. Power lines are still dangerous. If you grab a power line and your feet are touching the ground, you can still get a shock even if it's covered in rubber, even if it's fully coated and you're not touching the metal itself. Because again, forming a parallel circuit, some current can still go down the path of least resistance. You just want to make sure that the path of greater resistance is so great that it's not worth the effort. So, more of the current will go down path of least resistance. The amount of current that will go down the path of greater resistance is always proportional to the difference in the resistances. Again, the resistance down the 2K pathway is 5 times smaller than the resistance down the 10K pathway. So as a result, the 2K resistor is going to get 5 times more current in this configuration. But again, note that the two separate resistances here, 0.9 milliamps and 4.5 milliamps, both add back up to 5.4 milliamps. 0.9 plus 4.5 is 5.4. So Kirchhoff's laws still hold true here as well. The total circuit has a 9-volt drop, and the total circuit has this much current flowing through it. It's going to divide up into these two pieces that literally add back up to the same number before it comes back to the battery. So when you are working on examples of this, you want to make sure, if you're looking at specifically how the voltage gets divided up across a series circuit or how the current gets divided up across a parallel circuit, you want to make sure that all of your values across all your resistors add back up to the circuit totals. Kirchhoff's laws demand it, and it's a way for you to check your work. All right. Questions, needs, concerns, please let me know. I'm going to... There's one more example one more kind of thing I want to show today, but I'm realizing that I left the image out of my slideshow, so we'll pause for a sec while I get that together. Okay. All right. So, as kind of just a quick review of how to do hybrid circuits, we've looked at hybrid designs for capacitors. Wanted to quickly just show an example of one for resistors as well. The methodology for how to find the total effective resistance of this circuit is the same as before. You kind of want to start combining individual pieces together at a time and then slowly simplify it into a more simple whole. The only thing that's different is, again, just the logic of how the resistors add up with one another. So, quick sample, just involving some resistors in a hybrid configuration here. We have a current this will just be a quick demonstration. We have a parallel branch here between three different 30 ohm resistors. Current comes back together to a 5 ohm resistor. Then the current splits again to two different 10 ohm resistors before the circuit ends. So, to simplify this one, again, you want to kind of handle one rung, one little piece at a time. Simplify it just by one element until you have one total final resistance left. I'd recommend the first step in an example like this being to look at these three in parallel with each other, combine them into a single one, and look at these two in parallel with each other, combine them into a single one. So these three, 1 over 30 plus 1 over 30 plus 1 over 30 will be 3 over 30. Invert that to get 30 over 3. So this whole thing here can simplify to just 10. We'll leave the 5 as it is for right now. And then for the two 10s here, we'll have 1 over 10 plus 1 over 10. That'll be 2 over 10. Invert that, 10 over 2 is going to be 5. So we've combined the parallel rungs in on themselves. That leaves us with a 10, a 5, and a 5, all in series with one another. And for resistors, series is the easy one. Just add them all up. That will give us a combined total of 20. So methodology is still true. Just the logic of how to combine each component together is what is inverted. The homework for Chapter 17 will involve a few examples of, look at this complex circuit, figure out its total resistance, look at this circuit, figure out the voltage drop or the current through each piece. So I do recommend be glancing at the homework, be working on it slowly, make sure that the problems make sense to you as you look at them. We'll break here for today. Last thing to cover for Chapter 17 tomorrow will be electrical power and how we'll talk about the different applications of that particular term. Namely, I think the most useful one is how it affects your electricity bills. I'm going to try to give you some practical knowledge about how those are calculated, how you can kind of use knowledge to make your electric bill more affordable whenever you have to deal with that in the future. So that's what's to come. Let me know whatever you need. Be working on homework and quizzes and stuff. I won't be in this room today because I've got some errands that I need to start running shortly after this we break here right now. So if you have any questions, email me or let me know tomorrow. And we'll break here. If I don't hear from you later today, then I will see you tomorrow.